In this video, we are going to cover 9.4 chemical properties. At the end of this lesson, students should be able to explain the chemical properties with reference to nucleophilic addition with KCnH+ or NaCnH+, H2O, ROH, NaHSO3, and Grignard region RMGX. And secondly, predict the products formed by reaction of carbonyl compounds with regions in A1 Roman. We can simplify the reaction of carbonyl compounds into 4 categories. The first one is nucleophilic addition, reduction, condensation, and the last one, oxidation. In this video, we are going to focus on nucleophilic addition. First of all, we should ask this question: why carbon double bond oxygen is susceptible to nucleophilic addition? If we look at the structure of carbonyl compounds, the electron density is drawn more towards the oxygen atom, making the carbon atom deficient in electrons. This will make the carbon as a suitable electrophilic site. The carbon atom becomes the site for nucleophilic attack. When carbonyl carbon is attacked by a nucleophile, the carbonyl pi bond is broken and a tetrahedral intermediate is formed. Then the hybridization of sp2 carbon atom changes to sp3. In carbonyl compounds, aldehydes are more reactive than ketone in nucleophilic addition reaction. Why? Because the first reason is steric factor. If we compare the structure of an aldehyde and a ketone, aldehyde only have one alkyl group, while ketone has two alkyl groups. This means aldehyde has less steric effect, while ketone has more steric effect. This makes an aldehyde more reactive than a ketone. The second factor is electronic factor. Since aldehyde has only one alkyl group, but ketone has two alkyl group, this means that ketone has more electron donating group than aldehyde. So, the aldehyde will have a greater partial positive charge on its carbonyl carbon than a ketone because it has only one alkyl group that acts as an electron donating group. Nucleophilic addition reaction. Carbonyl compounds undergo nucleophilic addition reaction with A. NaCN or KCN with H+, B. H2O, C. ROH or alcohol, D. Sodium bisulfite NaHSO3, and E. Grignard region. The first one is the addition of NaCN or KCN with H+. The regions are aldehyde or ketone and NaCN or KCN with H+. The product will be cyanohydrine. The general reaction is as follows. If we look at the equations, when a carbonyl compound is react with NaCN and H+, the carbon double bond oxygen is lost, and the oxygen becomes OH, while another single bond from carbon attached to CN that is provided by NaCN. Another example are as follows. We can see that from the first equation, the carbon double bond oxygen is lost and the oxygen become OH, while another single bond from the carbon attached to the CN that is provided by KCN. The same goes for the next example. The carbon double bond oxygen is lost, the oxygen become OH, and another single bond from carbon attached to the CN that is provided by NaCN. So, from here we can predict that if carbonyl compounds react with NaCN or KCN with H+, the carbon double bond oxygen is lost, the oxygens now become OH, and another single bond attached to CN. The second nucleophilic addition is the addition of water. The reagents are aldehyde or ketone and water. The product will be hydrate or gem diols. The general reactions is as follows. If we have a carbonyl compound undergo reaction with H2O, the carbon double bond oxygen is lost and the carbon will be attached to two OH groups. Gem is the short form for geminal, which means two OH or X are bonded to the same carbon. So in this case, when a carbonyl compound undergo addition with water, the product is gem diols. The carbon is attached to two OH group. If we look at the examples, the first one we have methanol. When undergo nucleophilic addition with water, the carbon double bond O is lost and the product will be carbon that attached to two OH group. The same goes for the next example, butanone. The carbon double bond O is lost and now the carbon is attached to two OH groups. So, to conclude this, if we have carbonyl compounds react with water, the product will be gem diols, which means the carbon attached to two OH groups. The third nucleophilic addition is the addition of alcohol. We will look at the formation of hemiacetal and hemiketal. First, we look at the reaction between aldehyde and alcohol. When an aldehyde is react with an alcohol, the product will be hemiacetal, which means the carbon double bond oxygen is lost and the product will be carbon that attached to OH and another single bond attached to OR from alcohol. If we have a ketone that react with an alcohol, the product will be a hemiketal. The carbon double bond O is lost and now the carbon is attached to OH and another single bond attached to OR from the alcohol. under further reactions, the hemiacetal from an aldehyde can react with another alcohol and form a compound called acetal. The OH from the hemiacetal is now being replaced with OR from the second alcohol. While if we have a hemiketal from a ketone, if it undergoes reaction with another alcohol, it will form a compound called ketal. The OH from hemiketal is being replaced with OR from the second alcohol. The example is as follows. We have an aldehyde undergoes reaction with CH3OH, and we can see in the product the carbon double bond O is lost and the carbon is now attached to NOH and OCH3 from the alcohol. The fourth nucleophilic addition is the addition of sodium bisulfite, NaHSO3. The reagents are aldehyde or ketone and NaHSO3. The product will be bisulfate salt. This reaction is used for purification of aldehyde and ketone from other non-soluble organic compounds. The general reaction is as follows. We can see in the reaction that if a carbonyl compound reacts with NaHSO3, the carbon double bond O is lost. The oxygens now becomes OH and the carbon has another single bond attached to SO3 minus Na plus that is provided from NaHSO3. This product is called bisulfate salt. We can see from the examples as follows. First, we have ethanol that undergoes reaction with NaHSO3. The carbon double bond O is lost. The hydrogen from NaHSO3 goes to oxygens and it becomes OH, and another single bond from the carbon attached to SO3 minus Na plus. The same goes for the following example, which is a propanol. The carbon double bond O is lost. The hydrogen from NaHSO3 goes to the oxygens and it becomes OH, and another single bond from carbon is attached to SO3 minus Na plus. So that's how you predict the product of a reaction between carbonyl compound and sodium bisulfite. The last one is the addition of Grignard reagents. If Grignard reagents react with methanol, the product will be primary alcohol. If Grignard reagents react with other aldehydes, the product will be secondary alcohol. And if the Grignard reagent reacts with ketone, the product would be tertiary alcohol. First, we see the first reaction between Grignard reagents and methanol. We can see in the process that the carbon double bond oxygen in methanol is lost, and now the carbon is attached to the CH2CH3 from the Grignard region, while the oxygen is attached to MgBr. Upon hydrolysis, the OMgBr will become OH and the product will become primary alcohol. The second reaction is the reaction between a Grignard regions and other aldehydes such as ethanol. In this reaction, we can see that the carbon double bond oxygen is lost. The carbon is now attached to CH2CH3 from the Grignard regions and the oxygen is attached to MgBr. Upon hydrolysis, the OMgBr becomes OH and secondary alcohol is formed. The last one is the reaction between a Grignard region and a propanone, a ketone. We can see in the equation, the carbon double bond O is lost. The carbon is now attached to CH3 from the Grignard region and the oxygen is now attached to MgBr. Upon hydrolysis, the OMgBr becomes OH and a tertiary alcohol is formed. In summary, to predict the product from the reaction of Grignard regions and carbonyl compound, we should remember that the carbon double bond O is lost. The final product will be the carbon attached to OH and carbon that attached to alkyl group from the Grignard regions. That's all for this video. Thank you.